Cool. Maybe I'll start here on the overview while everything is downloading for everyone here. What we're going to be doing here, at least on the overview, is a few different things. Going through an overview of computer vision and NLP as it is today, the challenges in combining both, representation learning in computer vision, as well as representation learning using natural language processing. And then this is a demo that shows you how to build these together. So just to start here, to focus in on use cases for image search, many teams like Pinterest, Stitch Fix, Flickr, and more leverage deep learning to learn representations of their images and provide recommendations based on the contents that users find visually stimulating. So here's just a great demo showing from Pinterest of taking like an individual selection of an image, finding both not only of what is a text representation of that, but similar images that they also have within their backend. In addition, these representations allow consumers to efficiently search photo libraries for images that are similar to the selfie they just took, or for particular items, just as they were doing there. So this is going to be a tutorial of how we get this done. I'll skip this. I was saying this out loud. So let's just start here with a quick overview of computer vision tasks and challenges. So in the world of CV, there are two main ways of getting features from images. First is what I like to call, and it's called by the field, as white box algorithms. This is like taking normal image descriptors, finding differences between different pixels. These are algorithms that you can actually see and define yourself. And the second are on the black box algorithms that, while harder to interpret, are much more flexible when applied to different contexts. And that's one of the main reasons that we're focusing on black box algorithms. Can I see some hands of who's used like white box algorithms for computer vision in the past, like OpenCV and different things? Cool. And how many of you here are familiar with using different deep learning techniques for doing image processing and computer vision? Neat. So this is what we're going to be focusing in on here, and for the half of you-ish that have been working with different black box algorithms for basically image both classification or object detection, know that this started in 2012 with AlexaNet being published for image classification, which had a lot of use cases in both fashion and security. However, most applications where you're actually going to be applying these different deep learning techniques for computer vision require either object detection or segmentation, shown there like at the bottom with those cats and dogs. And this has many different real-world applications for medicine, real-time security, autonomous vehicles for doing perception of the environment around them, and different things here is like leveraging classification and localization. Some different common models you might have heard of are YOLO or RetinaNet. Now, for advanced applications that leverage deep learning-based CV models, these can include things like pose estimation, scene parsing, 3D point cloud estimation from 2D images. The variety is actually pretty large of what you can be able to do once you can do accurate either image classification or object detection here. And an example of this of like what you can do, just straight out of the box in a small 4-week project, we had an Insight AI fellow, Felipe Meja, he's now at In-Q-Tel, who developed a custom image classifying algorithm leveraging pose estimation to recognize gestures. So on the right, you can see an application for computer vision as if you wanted to not only do the pose of an individual human and then use that to actually direct like finger motion pointing towards a certain device to turn it on and off. So to dive into the next part for natural language processing tasks and challenges, many different traditional NLP tasks cover many domains, from text classification, spam detection, information extraction for text summarization, sequence-to-sequence learning for chat spots or translation. And I'll just kind of do a brief overview of this. So from the classification side, NLP classification tasks have historically relied on techniques including logistic regression or naive Bayes. However, this is starting to change. Really, we've seen this changing in industry. So Insight has worked with over 400 companies just here in the Bay Area alone. And over the past 3 years, we've seen pretty momentous changes, being able just to empower NLP models with things such as like transfer learning to allow data scientists to create NLP models for new domain with limited training data. So being able, if you're going to start, let's say, on medical classification, to leverage the entirety of PubMed to be be able to go and use this for like specific tasks. And that's including like leveraging other training corpuses. Wikipedia corpuses are often used here. So other NLP tasks include sequence-to-sequence models, which are used for translation and chatbots, but however they require really large data sets to be effective in covering the wide and broad range of the English language. That said, they can be used efficiently for data augmentation for training of other NLP tasks. So at the bottom here is just looking at, many of you have probably used chatbots online. They're actually kind of going out of vogue because they're not very flexible. But if you wanted to like talk to an AI agent for, I want to book a flight to Hawaii, being able to basically sample the space using deep learning of what that individual actually is looking to do. So like pairing like book to fly, travel, go, get. But there's only so much that you can do in the space without enough training data. So to launch into some of the challenges in combining both, let's start exploring how we combine these, and one case of this is image captioning. This process leverages deep learning to prime a language model with features derived from convolutional neural networks, then feeding individual images into this combined network of convolutional neural nets in series responsive long short-term memory blocks. As you can see from, this is actually a simplified version of this model. These models are really complicated. That's so while the results can be impressive for well-trained networks, it's quite difficult, like as an engineer or a data scientist, to make these models flexible, and it's really, really hard to debug them due to their complexity. So while this can work for kind of larger scale and specific applications for some of the larger tech companies, for those of you that are here with smaller companies, I just give you the fair warning that if you try and do this yourself, this isn't going to be a week-long project. It's going to be much longer than that. And again, talking about other use cases here for both CV and NLP. One of them that I really like, and I've seen there's a few different startups in this space, and we've had individual Insight Fellows tackle, is automated code generation. And a great use case of this is if like you were a UX designer and you wanted to actually take what you put down on the whiteboard and automatically generate the website that you want from these wire sketches. You can actually do this using the exact same image captioning modality, where you can both take an input image and you can feed it forward over time. That's so you have a convolutional neural net and also the memory responsive GRU network. And what you do is you basically feed this forward piece by piece to assemble a website. And the data that you use to match this are both whiteboard drawings and the actual HTML code that needs to be generated. That's so while, again, this model can be successful with enough training data, the model performance is really impossible to improve without adequate and really broad data of different possibilities, like basically of filling the possibility space with how you're going to correspond on the left, those hand-drawn wire sketches with on the right, actually creating a website. Cool. So a big thing that I want to emphasize here when tackling combining both modern computer vision and NLP approaches is how do you make it scale? There's many different methods to mix and match between different architectures, but if you would be going down this pathway in the future, or really in the entire realm of machine learning and AI, making sure to think about scalability before you even start building is a really important facet. And one of the things that we are trying to do in the future is like, the combined is to avoid this, of that many different combined representations of both images and text is in the past different techniques have learned to do this implicitly. So actually having all of the data that you want to do to map from A to B and backwards from B to A. But again, hard to cache and optimize, hard to use across services because these models are entangled. So what we're going to be doing here is learning what if we want to learn a simple joint representation between the two. Cool. So I know that we're dealing with slower Wi-Fi. Are there any questions before I get to the next spot in the workshop of having a next line of code for downloading some of the data sets that we'll be using? One second. Cool. So if you go, again, for the instructions just to start, Wi-Fi might be limited in the room, but if you go to bit.ly, ODSC-semantic/search, what you're going to be able to do from that is there is actually block by block code. The first thing that you'll need to do is actually do git clone and then cut and paste the name of the URL. That will actually allow you to pull in the repository most easily. Once you have that repository, you can actually then make a Conda environment specifically that you'll use for this. Is that helpful for you there?
Yeah, no, I just didn't take down the bit.
Cool. Cool. And in this entire, basically this entire talk for anyone here, that if you go to that link, it's just going to my colleagues, Emmanuel Mason's GitHub repository. That actually has the full walkthrough here. It takes about an hour and a half to run if you're on about a 1 megabit bandwidth. Downloading speed is what I calibrated it for, but obviously should have found either a smaller data set or a better way to get you all the data to do this. Other questions? Cool. So I'm just going to move forward then. Cool. So just to start here in the second part, talking about image search and in general in machine learning, and just like in software engineering, there are many different ways to approach a problem, each with different trade-offs. If we are doing research or local prototyping, we can get away with very inefficient solutions. But if we're building an image similarity search engine that needs to be maintainable, scalable, we have to consider both how we can adapt to both the data evolution, so if we want to add new images to our image search engine, and how fast our models can run. One of the things that you can see, or a good anecdote, is if you go to, let's say, if you go to Google Photos and you add in an image, you can immediately search against that through their back-end stream processing pipeline of basically pulling out features for you. So with these types of approaches is ways that you can get towards that level of scalability. So for those of you that got lucky enough with the internet to be able to download and basically create your Conda environment, these are going to be the next two things that you're going to need to do. Wait, where's the code part 3? Pass it. Cool. I must have skipped here the code part 2. Some of you might have already been doing this, but one of the things that we're going to be downloading to use here are these pre-trained glove vectors. These are the word-to-vec vectors that you can use here directly. You can curl it off of the Stanford website and then basically move it into the models repository. Once that has downloaded and you've moved those in, we have an example image data set that you can use that was kindly passed on to us, where you can make this individual data set. I have a Python downloader script which you can use, which basically sets this up and downloads it all. And then there's also a few more commands there at the bottom that you can cut and paste off of the repo just to do some renaming of some of the different folders that are there in that data set. Cool. So when thinking about how we were going to make an image search engine, I want us to think about a few different approaches, and I'm going to walk through these one by one. The first is that we can build an end-to-end model that is trained on all of our images to take first as an image as an input, so showing this cat reaching out, and output a similarity score over all of our images. So let's say we have 1,000 different images here. We'd output of each time that we put in this cat would be all of these images. Now, the advantage of this type of model, as you can imagine, is that the predictions happen really quickly. Basically just one forward pass. You're taking an image and then finding this. You're basically doing some processing to find the similarity. But again, the problem that this would happen here is that if we wanted to add a new image, like we had a new image of a cat, or let's say you wanted to add an image of your own cat, every single time that you would want to train a new model, we're going to need, every single time you want to add a new image, you'll have to train a new model. And you also reach a quick state with this that if you'd have so many classes that it would be extremely hard to optimize it correctly. So as you can imagine, this works well for maybe 100 to 1,000 total images. But if you're going to have, let's say, 1 million images of cats, this model breaks down really quickly. So the approach is fast but does not scale to large data sets. And in addition, we would have to label our data set by hand with the image similarities, which could be extremely time consuming. Again, as you scale, every single time that you would add a new image to it, you'd actually have to go back and do this manual relabeling. So let's think about a second approach that we could do. Another approach is to build a model that takes in 2 images and outputs a pairwise similarity score between 0 and 1 using Siamese networks. These models are really accurate actually for large data sets, but lead to another pretty key scalability issue, which is that we usually want to find a similar image by looking through a vast collection of images. So we have to run our similarities model once for each image pair in our data set. If our model, let's say, is a convolutional neural net, which we're actually feeding in to find the similarities. So as described before, this can be a convolutional neural net to like pull out the features of an image and say its competence of how those individual features or classes. And we have more than a dozen images. This also starts becoming quite computationally expensive. So the pros here is it scales to large data sets. Some of the cons here is that it's slow to work for, and also does not work for text here. So we can't actually, in this current model implementation, basically leverage text. Does anyone here that's worked with Siamese networks before have any experiences of what some of the different shortcomings are outside of these cons of being slow are for this? Because this is often implemented actually at scale for large companies. Any ideas? Well, with that awkward amount of silence, maybe I'll just go forward and give kind of what I think is one of the problems here. One second, as I push this in. One of the big problems here is actually negative data mining. If you can imagine that you're actually assigning labels between your individual images of their similarity score that you're using for training, these models actually become really sensitive to when you have overly positive or overly negative similarity scores. So if you have 2 images that like look by eye to be very visually similar, but their actual makeup, like the 2 photos could be taken in one in a dark and one in a light environment, and almost the exact same photo there, and you assign it a high similarity score, can actually really start breaking down your model with the similarity, and it becomes unstable while fitting the model. So for these type of model approaches for using Siamese networks, there's a lot of different data pruning and different steps that you need to actually make this work at scale. So this is a third approach, which is the one that we're actually doing here for those that are running through the GitHub repo, is that is a simpler method, which is similar to word embeddings. If we find an expressive vector representation or embedding for the image, we can then calculate their similarity by looking at how close the vectors are to each other. This type of search is a common problem that is well studied, and many libraries implement fast solutions. The solution that we're actually implementing here is using the library called Annoy. In addition, if we calculate these vectors for all images in our database ahead of time, this approach is both fast, one forward pass, and an efficient similarity search, and it's also scalable. So some of the different commands that we're actually about to get to are for actually indexing of these images in order to be able to do search much more quickly in the future. And finally, if we manage to find common embeddings for our images and our words, we can actually use them to do text-to-image search. And because of its simplicity and efficiency, the third method will be our focus. So again, just like looking at this to reiterate, we're going to take this image of a cat, we're going to find the embedding for each image, which is calculated ahead of time. And the pros, again, is scalable and fast, and the cons is, while these representations are pretty simple, I'll get to in a few minutes, actually, of what you can do even with a 1,000 image data set for training. So a question then that we're going to be doing is, how do we actually use deep learning representations to create a search engine? Our final goal is to have a search engine that can take in images and output either similar images or tags, and take in text and output similar words or images. To get there, we will go through 3 successive steps as on the screen, and these are also what are in the GitHub repo. First, you're going to search for similar images to an input image. Second is searching for similar words to an input word. And then lastly, you generate the tags for the images, and you can search the images using text. And not only can you search the images using text of single words, you can actually use multiple words together, and I'll go through how you do that. So the data set that we'll use to basically work here, and that you might be downloading now, consists of a total of 1,000 images divided in 20 classes with 50 images each. This dataset contains a category and a set of captions for every image. To make this problem harder and to show also how well our approach generalizes, we will only use the categories and disregard the captions. So we're actually not even going to leverage the captions. So there is actually, if you wanted to take new images, outside of just saying of what single class it belongs to, you have to do no additional data labeling. So in total, you're going to have 20 classes, which are listed out on that left-hand side there. Cool. And so what we're going to do is we're now going to load a model that was pre-trained on a large data set, ImageNet, and it's freely available online. In this code here, we use VGG16, but you can really use any other code, any other convolutional neural net architecture. And this approach, works and is scalable to different architectures. And we use this model to generate embeddings for our images. So again, we take our cat, and we put it into VG16, and then we get this last layer, which is our embedding, and then we can find out with a softmax of what is closest to in classifications. So what do we actually mean by generating embeddings? Again, this model is trained up to the penultimate layer and store the value of these activations. So I do have a little bit of time there, and one of the things is once we've used the model to generate image features, we can then store them to disk and reuse them without needing to do inference again. This is one of the reasons that so many different people that are in the world of NLP are leveraging embeddings, because it can be a really fast method and practical to get huge efficiency needs, being able to pre-calculate different parts of that network. Again, and on top of storing them to disk, we will build a fast index of the embeddings using Annoy to be also allow us to very quickly find the nearest embedding in any given embedding. So also a faster way to index. So if we do this here, we can show here our embeddings. Each image is now represented by a sparse vector of size 4096. And the reason the vector is sparse is that we have taken the values after the activation function, which zeroes out the negatives. So as you can see here, we have all of the individual output. So before, we have the different embedding layers that's going across the top, all 4096 of them, and then for each class going down 0 through 10 and beyond, we can actually go to 1000. We're able to do that calculation. Cool. So the code part 4 is that now that we've trained a custom model to map images to words, one of the things that we can do here, so this is how you would train a custom map to map images to words. The actual training step here, most of you are using probably computers that have somewhere between 8 or 16 gigs of RAM. If you only have 8 gigs of RAM, each epoch that you'd actually be doing for training takes around 20 minutes. So I'm going to actually have a way here that you can start downloading and not have to do this training yourself. And this is if you want to go and actually download a pre-trained model that you can use directly here. If you go to bit.ly, I use underscores here, ODSC _download _model. You'll actually go to a Google Drive page, which not only has the current repo that's live in the GitHub with all the information that you'll need, you can also download my model, my_model.hdf5. This is just a storage format. When you do this, this model is pretty large. It's about 500 megabytes, but if you start this now, you can move this then into the semantic search folder. Cool. Does that... Yeah. Yeah, so this is actually, if I go back. Cool. Yep, so this is actually training the model here for doing for the individual images on towards the embedding step, yeah. So it leverages both the name of the class and the glove vectors to do this training for you. Cool, so what this model actually enables you to do, for those of you that have the download of the model, is we can now simply take in an image, we can get in its embedding, and look in our fast index to find similar embeddings in the similar images. This is especially useful since image labels are often noisy, and there's more to an image than its label. For example, in our data set, we have both a class cat and a class bottle. Who of you here thinks this image would be labeled as bottle? Labeled as sink? Labeled as cat? That's what I would think too. That's why I have this example, and the correct answer though is bottle. As you can see, there's like a tiny little soap bottle at the top of the image. And this is because labeling images as unique categories can be quite limiting, which is why we hope to use more nuanced representations to be able to capture these differences. And this is exactly what deep learning is good at. Now let's see if our image search using embeddings does better than human labels for the cat bottle image. And great, what we can see here is that this is the new model that that you can be downloading now. And if you use this here to search of what this cat is most similar to, we mostly get more images of cats, which seems very reasonable. That our pre-trained network has been trained on a wide variety of images, including cats, and so it is able to accurately find similar images, even though it has never been trained in this particular data set before. However, that you can see here, one of the images in the middle of the bottom row shows a shelf of bottles. So while this approach performs well to find similar images, in general, we are only interested in the part of an image. That's so basically the subset of this image that we can actually pull out features from. So for example, given an image of a cat in a bottle, we might be only interested in similar cats, not similar bottles. So what we do here, and a common approach to solve for this, is to use an object detection model first, detect our cat, and do image search on a cropped version of the original image. While this adds a large computing overhead, we'd like to do this specifically. So in order to do this, I'm actually going to be to answer your question. This is actually a simpler hacky approach, is a semi-supervised search, which consists of reweighing the activations. And we do this by loading the last layer of weights we had initially discarded, and only use the weights tied to the index of the class we were looking for to reweigh our embedding. This cool trick was actually brought to both Manu and myself through a fellow Insight Fellow, Daewon Ryo, who is now at Headspin. So thanks so much to her. And for example, in the figure, we use the weights of the Siamese cat class to reweigh the activations on our data set, shown in green. Cool. So we could use an object detection model, like basically an image search on a cropped image, but instead we kind of use a bridged approach, which can be hacky but efficient to reweigh the activations. And so we can put in both an image and an individual piece of text and map that to the weighted embedding. Cool. So when we do that and actually put in the word cat, we can see that the search has been biased to look for Siamese cat-like things. We no longer show any bottles, which is great. You might, however, notice that the last image is of a sheep. This is interesting, as biasing our model has led to a different kind of error, which is more appropriate for our current domain. Cool. And we have seen that we can search for similar images in a broad way, and condition on a particular class our model was trained on. And while this is, oops, am I backwards? There we go. And while this is like a big step forward, we want to just be able to put in just one image and not both image and text. Cool. So in order to do this, we're going to use more than simple tricks and leverage a model that can understand the semantic power of words. That model, so basically, taking a detour to the world of natural language processing, we can use a similar approach to index and search for words. We can load a set of pre-trained vectors from Glove, which are obtained by crawling through all of Wikipedia and learning the semantic relationships between words in that data set. And then just like before, we will create an index, this time containing all of the Glove vectors. Then we can search our embeddings for similar words. And then we can also then use the distance between these embeddings as a method for search. And because our representations for words and images, though, one of the things that's important to note is that they're going to be different sizes. So the embeddings for our images are size 4096. That is the total ImageNet class size, while those for words in that specific Glove basically model that you downloaded are size 300. And both models are changed in different, basically in a different fashion. So to combine these two, we basically need to do something a little bit hacky again. Even if both embeddings were the same size, we need to train this joint model. So this is actually leveraging a paper that is now a little bit outdated in different approaches, but this is what is implemented here, is the Device paper, a deep visual semantic embedding model, which we use here, and that's the model that you were downloading. And while we're not re-implementing it exactly, we will heavily lean on its main ideas. Cool. So the idea is to combine both representations by retraining our image model and changing the type of its labels. How many of you with the internet were able to get to the part where you can download the model? Cool. One. So for the lucky one or two of you that I saw raise your hand, you can continue to go through the code here. And that's basically now that you actually have the model, you can index these images using the custom trained file. And you can also see how it works to search for an individual image here, like that's the cat in the data set, or search for an image using words. But what's actually happening here again for this devised paper is usually image classifiers are trained to pick a category out of many, like 1,000 for ImageNet, and what this translates is the last layer is a vector of size x, like 4096, representing the probability of each class. So the one on the left there can be 4096 or 1,000, and this means our model has no semantic understanding of which classes are similar to others, such as classifying an image of a cat as a dog results in as much error as classifying as an airplane. So on the right there, for our hybrid model, we replace this last layer of our model with the word vector of our category. This allows our model to learn to map the semantics of images to the semantics of words. It means that similar classes will be closer to each other, as the word vector for cat is closer to dog than airplane. Instead of a target size of 1,000 with all zeros except for 1, we will predict a semantically rich word vector of size 300, as shown there at the far right at the end of that deep learning model. Cool. So again, we retrain our model on a training split of our data set. That's what the training code actually does in the repository there to learn to predict the word vector associated with the label of that image. For an image with the category of cat, for example, we were trying to predict the 300 length vector associated with cat. This training takes a bit of time, as I mentioned before, so that's why you have the opportunity to download the model directly. One thing I want to note is how ambitious of an approach this is compared to other types of combined computer vision and NLP problems. The training data we are using here that you can use yourself to train is really, really small compared to classical approaches, just 800 images. While ImageNet, for instance, the baseline actual like weights and activations of ImageNet in VGG16, you'll have 1 million images that will be basically going into that. That's 3 orders of magnitude more. If we were using a traditional technique of training with categories, we would not expect our model to perform very well in the test set, just with these 800 images, like evaluating on 200, and we would certainly not expect it to perform at all on completely new examples. So what we do here is once our model is trained, we have our glove word index from above, and we built a new fast index of our image features by running all of them through the data set and saving it to the disk. So taking this image here of the interior of a fridge, we can now easily use this model to extract tags from any image by simply feeding our image to our trained network, saving the vector of size 300 that comes out of it, and finding the closest words in our index of English words from glove just using cosine similarity. So this is an image that actually comes from the bottle class, and let's see if what our new approach can actually output. So those are the generated tags. Not surprisingly, it has bottles, but many other things as well as here, cans, vodka, jars, whiskey, and more of what it thinks is actually here. And this is a pretty awesome result, as most of the tags are super relevant to what's actually in the fridge. And while the method still has room to grow, it picks up on most of the items in the image fairly well, and the model learns to extract many relevant tags, even from categories that it was not trained on. Cool. What we can do now is also use our joint embedding to search through our image database using any word, not just the words that were actually part of the class. We simply need to get our pre-trained word embeddings from glove and find the images that have the most similar embeddings, which we get running through our model. Let's start first with the word that was actually in our training set by searching for dog. Cool. Pretty good results. But a big question that you'd have there is whatever. That's just one word that you trained on. Can you get this from any classifier that was just trained on, just the labels? So let's look here for ocean. And this is when it starts getting pretty cool. You can actually use a word that was not in our training set, is leveraging water, and our model just understands without implicit connection between this word ocean and what an ocean actually is, that an ocean is similar to water and returns many items from the boat class. Cool. How about another? Let's try the word street. You can also do this using like the command line options if you have gotten to that point in the GitHub repo. And for street, what we actually see here is our return images come from plenty of different classes: car, dog, bus, person. Yet most of them contain or are near a street, despite us having never used that concept when training our model. And because we are leveraging outside knowledge, so the glove vectors trained in Wikipedia, these word vectors learn a mapping from images to vectors that is more semantically rich than a simple category, and it allows our model to generalize well to outside categories. So the next step, what we want to do is not just do like a single input word. We actually want to put in multiple words like cat lying on a sofa. And this is something before we started tackling this project in Insight, or really reading through a couple of different papers in the literature. Best ways to do this is I would not think that it would work to just take your word embeddings that you have there and just doing an average between the two that you can get out multiple words. So cat line on a sofa, there's no word in the English language for that yet. So what we're going to do is we're going to take the word for both cat and both sofa and then leverage the arithmetic properties of these individual word vectors. And what it turns out is that summing just these two word vectors alone works super well. So if we were just to search for our images by using the average word vector for cat and sofa, we could hope to get images that are very cat-like and very sofa-like. And this results here is that these images contain some version of a furry animal on a sofa, like the leftmost image on the second row is actually just, I think, filling for an individual pillow. And then our model, which was only trained on single words, can handle a combination of two words. And that, like, while this is not Google image search in its entirety, it's definitely impressive for a relatively simple architecture. Cool. I'm happy that, so we're at basically the 1 hour time point of where we are here. And you can actually pull up the entire demo once you've gotten to this point at the end. You can train and run this using a library called Streamlit, kind of similar to Jupyter, but it has a slightly different execution engine. But all you would need to do is just run this command in your command line, python demo.py, and then basically put in the different, you could even run that. All of these are actually hash arguments for argparse. And then this is basically going to get you these results and show you a readout of this entire demo here today. Cool. So other questions before I kind of keep on going. I'm happy to kind of talk with individuals about building your own image search pipeline, some of the different models here. Any questions?
So here the ranking is done on like a semantic score?
Yeah, for the cosine similarity, exactly, yeah. I'm not as knowledgeable of what Annoy does to actually index those to quickly be able to retrieve it, but you can see if you run this, if you run this on the command line, that it takes like only a second or two to actually return back those results. And when we weren't using Annoy, I think it was a little bit over 10 seconds of not having like an optimized approach to return those.
So it's more like a pixel-to-pixel similarity or like that?
Oh, you mean the similarity between the actual images? Yeah. So leveraging there basically, like for the images, if you want to do this, like leveraging just the features that we basically take out. Because basically what we can have here is like if we just had ImageNet here, like the mapping that we're going to do is just taking that almost last activation layer, where we just have the mapping to the individual classes in ImageNet, like basically, is this a dog, an airplane, a boat, bicycle, anything like that. But the mapping that we actually do for the model on the right, which is the one that you download, is mapping it against the embedding space that you actually get from the glove vectors. So you take an image and you basically map that back down to what would be closest, like for those actual embedding space for the glove vectors, and that's what you're comparing it against. So you're taking an image and embedding it into a word space. So it's different than taking like an image and like that 1 times 4096 layer is like, and before, like those different layers before are different parts of the image features, but this is like a way that you can build image search and map it against like the text, like basically the text space instead of image space. Feel free to ask another question. That's perfectly fine.
So did you try like the waterway instead of the glove?
So for this one, we just tried the glove vectors here. I haven't had a chance to try for different, basically either weighting or embedding space, but that's something that you can pretty easily implement here. The only changes that you need to make is like getting that actual model there, and depending on basically what that end layer is for that specific model, like changing some of the, you can tune this all. It's all done in Keras here. So basically being able to tune that last layer and by its size one.
So using the last layer and the global the last the matrix and just the mapping, just the three.
Yeah, exactly. So going and finding that mapping like between the two there. So basically compared to just like the feature space of comparing against like the ImageNet last classes there, but to the different space. Sorry if I didn't answer your question well last time. Cool. Cool, that's basically it on my side. If any of you are still working through that individual repository, I'm happy to kind of stick around for questions. But thank you so much, everyone, for coming by and learning a little bit more.